After the discussion on the polarization of dielectrics in a uniform electric field of a charged parallel plate capacitor, we consider other examples to study the electric field in insulating materials. We start with the case of two parallel infinite plates with the constant charge densities positive and negative sigma prime. We already proved that if there is only a vacuum or air between the infinite parallel planes, then the electric field E0 due to the opposite charges distributed uniformly over the planar surfaces is a uniform vector field pointing from the positively charged plane to the negatively charged one, and its magnitude between the plates is given by the surface charge density sigma over the dielectric constant epsilon naught of a vacuum. The electric field strength E0 vanishes elsewhere. In this example, the electric field is characterized by both the field strength E0 and the electric displacement D0 that is equal to the vacuum permittivity times the field strength E0. If a homogeneous and isotropic dielectric is introduced into the electric field E0, then the insulating material becomes polarized due to this field, and bound or polarized charges appear on the surface of the dielectric with the negative and positive surface charge density sigma prime. These bound charges produce a field strength E prime inside the dielectric with the magnitude of sigma prime over epsilon naught. Outside the dielectric, the field strength E prime is equal to 0. Since E0 and E prime are in opposite directions, the magnitude of the resultant field strength E inside the dielectric is equal to the difference between the magnitudes of E0 and E prime. If we substitute the expressions obtained for the magnitudes of E0 and E prime into the right-hand side, then the magnitude of the electric field E can be written as 1 over the vacuum permittivity epsilon naught, times the difference between the surface charge densities sigma and sigma prime. Outside the dielectric, the magnitude of the electric field E is equal to the magnitude of the electric field E0. Because the polarization field produced in the dielectric by the resultant electric field is perpendicular to the boundary surface of the dielectric, the normal component of the electric field is equal to its magnitude. We already saw that the polarization P in a linear and isotropic dielectric is equal to the vacuum permittivity epsilon naught, times the electric susceptibility chi E of the dielectric, times the electric field strength E. We also proved that the polarization surface charge density sigma prime at the boundary of a dielectric is given by the component of the polarization field P in the direction of the normal vector pointing outward from the surface of the insulating material. Then the polarization surface charge density sigma prime can be written as epsilon naught times chi E, times the magnitude of the electric field strength E. By substituting this result into the equation obtained for the magnitude of the electric field E, we can write the later as the difference between the magnitude of E0 and chi E times the magnitude of the electric field E. If we solve this equation for E, then we can state that the magnitude of the net electric field E in a polarized dielectric is equal to the magnitude of the external electric field E0 applied to the dielectric, over 1 plus the electric susceptibility chi E of the insulating material, or the magnitude of E0 over the relative permittivity epsilon R of the dielectric. The relationship between E and E0 shows that relative permittivity measures how much the electric field is weakened in a homogeneous and isotropic dielectric with an infinite extension inserted into the space between two uniformly charged infinite planes. In order to determine the electric displacement field inside and outside the dielectric, we consider the relationship between the electric field strength and the insulating material and a vacuum or air, stating that the magnitude of the field strength E is equal to the magnitude of the field strength E0 divided by the relative permittivity epsilon R of the dielectric. Now we multiply this equation by epsilon naught times epsilon R, where the left-hand side becomes epsilon naught times epsilon R times the magnitude of E, and the right-hand side is equal to epsilon naught times the magnitude of E0. In the left-hand side of this equation we can recognize the magnitude of the electric displacement D, whereas the right-hand side can be identified as the magnitude of the electric displacement D0 outside the dielectric. This result indicates that the electric displacement inside the dielectric between the infinite parallel surfaces is the same as the electric displacement of the external field produced by the homogeneous surface charge distribution over those surfaces. Since the magnitude of D given by epsilon naught times the magnitude of the electric field E0, where E0 is equal to the surface charge density sigma over epsilon naught, we conclude that the magnitude of the electric displacement D of the field, which is also the electric flux density of the field, is equal to the surface density sigma of the free charges uniformly distributed over the two infinite planar surfaces. In the case under consideration, the homogeneous and isotropic dielectric completely fills the part of the space where the electric field produced by the free charges is different from zero. This is the situation if there are no gaps between the infinite planes and the boundary surfaces of the dielectric seen in the figure. Then the magnitude of E is equal to the magnitude of E0 over epsilon R, and the vectors E, E0, E' and D are parallel with each other. A similar result is obtained if the homogeneous and isotropic dielectric does not completely occupy the space between the two parallel planes where E0 does not vanish, but only a part of this space that is determined by the equipotential surfaces of the electric field due to the free charges. In the figure, the vertical boundary surfaces of the dielectric are also equipotential surfaces of the electric field. In fact, we already obtained these results for charged parallel plate capacitors with a dielectric between their plates, where we assume that the electric field is approximately uniform between the plates if the distance between the plates is much smaller than their dimensions. These results, however, do not hold in the case when the homogeneous and isotropic dielectric does not completely fill the space defined by the electric field of free charges, or the volume enclosed by the corresponding equipotential surfaces. Then the vectors d and epsilon naught times E0 are not coincident, and the field strength E inside the dielectric is therefore not equal to the field strength E0 produced by the free charges divided by epsilon naught. This figure shows the electric field in a dielectric layer that is inclined with respect to the parallel plates carrying the free charges. As indicated by the field lines, the vector E' is perpendicular to the surface of the dielectric, hence the vectors E and E0 are not parallel with each other. The direction of the vector d is the same as that of the vector E, since the polarization vector P is proportional to the vector E for homogeneous and isotropic dielectrics. Consequently, the directions of the displacement vectors are different outside and inside the dielectric. It can be shown that they have different magnitudes as well if the boundary conditions are established for the vectors E and d on the surface of the dielectric. We will study such boundary conditions after presenting some examples for the electric field in bodies made of insulating materials. In the first example, let us consider a conducting sphere of radius R with a positive electric charge Q that is surrounded by an infinitely large homogeneous and isotropic insulating medium of electric susceptibility Chi and relative permittivity εr. We already proved that a charged conducting sphere produces an electric field in a vacuum or air as if all of its net charge were concentrated at its geometric center. Thus, at a point P at a distance r from the center of the sphere, the magnitude of the electric field strength E0 is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge Q over the square of the distance r. We also saw that the field strength vanishes inside the conducting sphere. Under the influence of the field of the charged sphere, the dielectric is polarized and the bound charges Q' appear with the opposite sign to Q over its surface in contact with the sphere, which can be described by the polarization surface charge density sigma prime. The later is equal to the electric susceptibility Chi of the dielectric, times the vacuum permittivity epsilon naught, times the net electric field E over the surface of the sphere evaluated at the radius R of the sphere. The total amount of polarization charge Q' over the surface of the sphere is equal to the polarization surface charge density sigma prime, times the surface area of the sphere, that is 4 pi times the square of the radius R. If we substitute the expression for sigma prime into this equation, the polarization charge can be written as 4 pi times R squared, times Chi E times epsilon naught, times the magnitude of the net electric field E evaluated at R. The magnitude of the electric field strength E' at the point P due to the polarization charges Q' distributed over the surface of the sphere is equal to 1 over 4 pi epsilon naught, times the amount Q' of the polarization charges over the square of the distance r. By substituting the expression obtained for the polarization charge Q' into this equation, we can write the magnitude of E' as Chi E times the ratio of R squared to r squared, times the magnitude of E evaluated at R. Here the magnitude of the net electric field E given by the difference between the magnitudes of E0 and E' is equal to 1 over 4 pi epsilon naught, times the amount Q of the charges carried by the sphere over the square of the distance r, minus Chi E times the ratio of R squared to r squared, times the magnitude of E evaluated at R. Since the fields E0 and E' decrease in inverse proportion to the square of the distance from the center of the sphere even in the dielectric, this must be the case for their superposition, that is the net field E as well. Then we can write that the ratio of the magnitude of the electric field E evaluated at the radius R to its magnitude evaluated at the radius r, is equal to the ratio of r squared to R squared. As a result, we can express the magnitude of E evaluated at r as the ratio of R squared to r squared, times the magnitude of E evaluated at R. We can recognize the right-hand side of this equation in the second term an expression obtained for the magnitude of the net electric field E evaluated at r, and write it as the difference between the magnitude of the electric field E0 and the electric susceptibility Chi E times the magnitude of the electric field E evaluated at r. If we solve this equation for E0, then the magnitude of the electric field produced by the free charges Q on the surface of the conducting sphere can be written as 1 plus the electric susceptibility chi-e of the dielectric, times the magnitude of the net electric field E. Or the magnitude of the net electric field E is given by the magnitude of the electric field E naught over 1 plus chi-e, that is the magnitude of E naught over the relative permittivity epsilon r of the dielectric. Consequently, the magnitude of the electric displacement D given by epsilon naught times epsilon r times the magnitude of E is equal to epsilon naught times the magnitude of E naught, which is equal to the magnitude of the electric displacement D naught produced by the free charges Q. As in the case of the dielectric layer inserted between the charged infinite planes, the insulating medium completely fills the region of the space where the electric field E naught due to the free charges does not vanish. The equations also show that the electric fields E, E naught and E prime, and the electric displacement field D are parallel with each other. Then these results are exactly the same as those obtained for the polarized dielectric between the oppositely charged infinite parallel planes. In the next example we determine the electric field in thick spherical dielectric shells enclosing a charged conducting sphere. Here we consider a conducting sphere of radius R with the positive charge Q that is surrounded by two thick spherical shells made of homogeneous and isotropic insulating materials with the relative permittivity epsilon sub R1 and epsilon sub R2. The outer radii of the shells are denoted by R1 and R2. In a vacuum the charged sphere produces the spherically symmetric electric field E naught pointing outward outside the sphere. Inside the conducting sphere the electric field and the electric displacement vanish. The electric field polarizes the dielectric shells that produces the surface charge densities sigma prime 1 and sigma prime 2 over the boundaries of the thick shells. If we apply Gauss's law for a spherical Gaussian surface enclosing the sphere and the shells, then we can write that the surface integral of the electric displacement field D over any such closed surface is equal to the free charge Q within that surface. Since the displacement field is spherically symmetric, the surface integral is given by the magnitude of the displacement field D over the Gaussian surface, times the area of the surface, that is 2 pi times the square of the radius r of the sphere that is greater than the outer radius r2 of the outer shell. But we already saw that the electric displacement is independent of the properties of dielectric materials and their presence can be ignored. Hence this equation holds everywhere outside the charged sphere, and we can express the magnitude of the electric displacement D at any point P outside the sphere as 1 over 4 pi, times the charge Q over the square of the distance r of the point from the center of the sphere. This equation does not contain any constant describing the properties of the dielectric shells, and the displacement field D in the shells is equal to the displacement field D naught in a vacuum. The formula also shows that the magnitude of the displacement D at the radius R of the conducting sphere gives the ratio of the free charge Q to the surface area of the sphere, that is the surface charge density sigma of the free charges. The relationship between the net electric field and the inner dielectric shell is given by the formula stating that the displacement vector D is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon sub R1, times the net electric field E in the shell. If the absolute dielectric constant of the insulating material in the shell, that is the product of epsilon naught and epsilon sub R1, is denoted by epsilon 1, then the magnitude of the displacement D can be written as the absolute permittivity epsilon 1 times the magnitude of the electric field E in the shell. As a result, the magnitude of the electric field E at any point P in the inner shell made of dielectric material is given by 1 over 4 pi times the absolute permittivity epsilon 1 of the dielectric, times Q over the square of the distance r of the point P from the center. The net electric field E in the shell is obviously the superposition of the field E naught due to the free charges Q and the electric field E prime due to the polarization surface charges sigma prime over the boundary of the inner shell at the surface of the conductive sphere. We can write a similar expression for the relationship between the displacement and the electric field in the outer shell, and state that the magnitude of the displacement D is equal to the absolute permittivity epsilon 2 of the dielectric material in the shell, times the magnitude of the electric field E in the shell. Then the magnitude of the electric field strength E has the same expression as in the case of the inner shell, where the absolute permittivity epsilon sub R2 appears in the multiplication factor instead of epsilon sub R1. The net electric field in the outer shell is the superposition of the electric field E naught, the electric field E prime and the electric field E prime 1 due to the polarization surface charge density sigma prime 1 over the boundary between the two shells at the radius R1. Outside the shells the displacement D is equal to epsilon naught times the electric field strength E. Hence, the magnitude of E at any point P outside the outer shell is given by 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge Q over the square of the distance r between the point P and the center. Evidently, the superposition of the electric fields E' and E'1 with the field E'2 due to the polarization surface charge density sigma'2 over the boundary at the radius R2 vanishes, and the net electric field is equal to E0 due to the free charges Q. That is, the electric field in this region is the same as the field of the point charge in a vacuum. Here we show the field of the electric displacement D for the whole space that is produced by the conducting sphere of radius R carrying the positive charge Q. As already mentioned, the field vanishes inside the conducting sphere. Outside the sphere it is a spherically symmetric field pointing outward with the magnitude inversely proportional to the square of the distance from the center of the conducting sphere. Its direction at any point P is determined by the position vector r of the point with respect to the center. The dielectric shells have no any role for the displacement field around the charged sphere whatsoever. The case is different for the electric field due to the free charges of the conducting sphere. Although the field also vanishes in the conductor, it is described by a different expression in each region outside the sphere. The electric field outside the conductor is still spherically symmetric and its magnitude is inversely proportional to the square of the distance from the center. However, it is discontinuous not only over the boundary between the conducting sphere and the inner shell, but also over the boundary between the two shells and the outer boundary of the outer shell. This fact is the direct consequence of the presence of the different dielectric constants in the expressions shown for each region. The ratio between the magnitudes of the electric field for the two sides of the boundaries is given by the inverse ratio between the dielectric constants at the two sides of the interfaces between the different media. In the previous examples, the electric field produced by the bound charges differs from zero only within the dielectric due to the shape of the polarized dielectric material. However, in general the electric field E' does not vanish outside the polarized dielectric. In the next example, we consider a dielectric rod which a uniform electric field E0 is applied to such that the symmetry axis of the rod is parallel with the field lines. Due to the polarization of the dielectric material in the body, opposite electric charges will appear at the two ends of the rod. Outside the rod, the electric field E' produced by these polarization charges is the same as the field of an electric dipole. As the figure shows, the resultant electric field strength E is greater than the external field strength E0 in the vicinity of the two ends of the rod. In the middle region around the rod, the net electric field E is weaker than the electric field E0 applied to the dielectric. Some of the electric field lines originating from and terminating at the polarization charges on the base faces at the two ends of the rod run inside the dielectric, where the electric fields E' and E0 have opposite directions. As a result, the net electric field E is also weaker than the external field E0 in the dielectric. The effect where the electric field due to polarization reduces the strength of the electric field applied to the dielectric is also called polarization screening or depolarization. The resulting field strength is usually not uniform outside or inside the body. The electric field produced by a polarized dielectric acting against the field polarizing the dielectric obviously depends on the orientation and the shape of the dielectric material. Consequently, we need to introduce a second-rank tensor called depolarization tensor to characterize this effect, which is defined by the equation stating that the electric field E' due to polarization is equal to -1 over the vacuum permittivity ε0 times the contraction of the depolarization tensor n with a polarization field P in the dielectric. This equation can be expanded in any Cartesian basis adapted to the symmetry of the problem, stating that the I component of the electric field E' is given by -1 over ε0 times the sum of the tensor component n sub ij times the j component of the polarization vector P, where the indices I and j are x, y, and z. As a special case, we consider an ellipsoid made of an isotropic and homogeneous dielectric material, and apply a uniform electric field E0 to it that is parallel with one of the principal axes of the ellipsoid. Then the matrix representation of the depolarization tensor can be diagonalized in the principal axis system of the ellipsoid, and it is enough to use only its three principal values to determine the components of the electric field E'. If any of the coordinate axes is directed along the polarization vector and the corresponding principal axis of the ellipsoid, then we obtain a simple vector equation stating that the electric field E' is equal to -1 over ε0 times the product of the corresponding principal value of the depolarization tensor n and the polarization vector P. In this case the principal value n is called the depolarization factor of the dielectric ellipsoid. For a homogeneous and isotropic insulating material where the polarization vector P is proportional to the uniform electric field E0 applied to the ellipsoid in the direction of one of its principal axes, this result tells us that the net electric field E due to depolarization is also uniform in the ellipsoid, and opposite to the field E0. Consequently, in the case of a homogeneous and isotropic dielectric ellipsoid aligned with the external field E0, The net electric field E given by the superposition of the fields E naught and E prime can be written as E naught minus 1 over epsilon naught times n times p. For a linear dielectric, the polarization vector P is given by the vacuum permittivity epsilon naught times the electric susceptibility chi E of the dielectric times the net field strength E in the dielectric. Then in the right-hand side of the equation we have E naught minus chi E times n times E. We can express the net electric field E from this equation as the electric field E naught divided by 1 plus the depolarization factor n times the electric susceptibility chi E. We also know that the relative permittivity epsilon R of the dielectric is equal to 1 plus the electric susceptibility chi E, which gives E naught over 1 plus n times epsilon or minus 1. In the special case of a dielectric sphere, all the principal values of the depolarization tensor are equal to 1 over 3, that is the depolarization factor n in the last equation is given by 1 over 3. Then for a sphere we can write the net electric field E as 3 times over epsilon R plus 2, times the electric field E naught. This formula is also valid if the uniform electric field E naught exists in a medium with a dielectric constant epsilon 1 instead of a vacuum, that surrounds a sphere with a dielectric constant epsilon 2. We only need to write the ratio of epsilon 1 to epsilon 2 instead of epsilon R in the formula. If this ratio is greater than 1, the resultant electric field E is weaker than the electric field E naught applied to the medium and the sphere, otherwise E is greater than E naught. The figures illustrate the two cases with the distribution of the electric field lines in the dielectric sphere and the medium surrounding it.